Dear students, very good afternoon. In the last session, we discussed about radiation resistance of the short dipole, and you understood what is short dipole, what is the importance of the radiation resistance in the impedance matching, and how to derive the expression of the radiation resistance of the short dipole. What are the stages required in the derivation of an radiation resistance of the short dipole? Similarly, in this session, we are going to discuss about radiation resistance of the half a dipole, which is also called as the lambda by 2 antenna. So half a dipole means the length of the dipole is lambda by 2. So here we are going to derive the expression of the radiation resistance of the lambda by 2 antenna as 73 ohms. So your requirement is to prove the radiation resistance of the lambda by 2 antenna is 73 ohms. Compare this with the radiation resistance short dipole. Radiation resistance of the short dipole is 80 pi square L square by lambda square. That is the radiation resistance of short dipole. We are using the same steps, but stages, instead of stages, we are going the steps here. The 4 steps are required to derive the expression of the radiation resistance of the lambda by 2 antenna. Dear students, if you understand the step, then it is very easy to derive the expression of this radiation resistance of the lambda by 2 antenna. So what are the 4 steps required to derive this expression? First step is calculate the electric field. See, electric field in the short dipole is different from electric field in the half a dipole. This is the first step. And second step is calculate the average radiating power density. So average radiating power density is denoted by W average. Next step is calculate the radiated power using this average power density. See, using this average power density, we can calculate the radiated power is equal to average power density, which is integrated over the elementary surface area, ds. Fourth step is calculate the radiation resistance by comparing equation A, where you calculated the radiated power, with the radiated power which is expressing in terms of the radiation resistance as P radiated is equal to 1 by 2 into I naught square into R. So call it as equation A and equation B. Finally compare the two equations, so I will derive the expression of the radiation resistance. So look here, electric field for the half a dipole or lambda by 2 antenna is given by 60 I naught by R into cos pi by 2 into cos theta. So you have to keep this standard equation of the electric field in your memory. So this one and electric field in short dipole, you have to keep it in your memory. Remaining is very simple. So how to find the average power density? Average power density is given by half into real part of vector E into vector H. Okay, so then half into real part of E theta is the component of the electric field, which is in the direction of the theta, that is E theta into A theta, and H is the magnetic field. This magnetic field is in the direction of the pi direction, is in the direction of pi, or is in the pi direction. So this H can be expressed in terms of the E theta by using the impedance equation. Eta is equal to E theta by H pi. Okay, E theta by H pi or E by H. From that we can write vector H is equal to E theta by eta into A pi vector. So next the average power density becomes 1 by 2 eta into E naught square into A theta into A pi. Okay, so multiply E theta with E theta, you will get E theta square, and eta you can take outside as a constant, and the half into real part of E theta into A theta into E theta by eta into A pi becomes 1 by 2 eta into E theta square into A theta into A pi. So average power density becomes 1 by 2 eta into E theta square into AR. AR is the dot product of A theta and A pi. Okay, and now we can find out radiated power using this average power density. We know that radiated power is equal to integration of W average into ds. So W average is 1 by 2 eta into E theta square into r, and ds is r square sin theta d theta d pi. As I told you in the short dipole also, ds is the elementary surface area in the spherical coordinate system. Elementary surface area in spherical coordinate system is given by r square sin theta d theta into d pi. So then P radiated can be calculated as integration of theta is equal to 0 to pi and pi is equal to 0 to 2 pi into r square by 2 eta into 60 I naught by r into cos of pi by 2 into cos theta whole square into ar into sin theta d theta d pi, and it becomes equivalent to finally it becomes equivalent into 36.56 after simplification and after integration and after substituting the upper and lower limits, and finally we will get radiated power is equal to 36.56 into I naught square. Okay, this you call it as equation number A. So radiated power P radiated is equal to 36.56 into I naught square is the equation A. Okay, and next we are going to write the equation of the radiated power, which is expressed in terms of the radiation resistance, as P radiated is equal to 1 by 2 into I naught square into Rr. Dear students, please note down the difference in the P radiated, okay, in short dipole and half-wave dipole. In the half-wave dipole, P radiated is equal to 1 by 2 into I naught square into Rr, but in the short dipole we had P radiated is equal to I naught square into Rr. This is the major difference between P radiated in short dipole and half-wave dipole. If you know this difference, you can easily derive the expression of either short dipole or half-wave dipole. Very easily. Now call it as equation B, then compare the equation A with the equation B. We get half into I naught square into Rr is equal to 36.56 into I naught square. Okay, then cancel I naught square on both sides and do the simplification, evaluate Rr. Okay, you will get Rr is equal to 2 into 36.56, which is equivalent to 73.12 ohms. Actually, radiation resistance should not be 73 ohms, it should be 73.12 ohms, and it is approximately, we are telling, the radiation resistance of the short dipole is 73 ohms. Actually, radiation resistance short dipole is not equal exactly 73 ohms, it is 73.12 ohms, but it is approximated as 73 ohms. Okay, this is also very important for examination point of view. So you have just dear student, try to compare the steps in short dipole and this half-wave dipole, then you can easily derive the expression of the radiation resistance if they ask in short dipole or they ask in the half-wave dipole. Thank you.